Hydraulic fractures are very important in many applications of petroleum engineering. And here we're going to see the example of how hydraulic fractures are important in well testing. For this particular application, here I have summarized three typical applications that include hydraulic fractures. And those are the leak of test, the diagnostics fracture initiation test, and the step rate test. And as you can see, they are useful for drilling, completions, and fluid and injection and disposal, and EOR respectively. Let's start with the leak-off test. The leak-off test is done when we drill a wellbore. In this case, what we do, as you can see it in this schematic, is to isolate the end of the wellbore before we continue drilling. We can use some packers to isolate that volume, and we inject drilling mud and pressurize the drilling mud in this closed cavity now until the wellbore fractures. And we want to measure that value for fracturing because that helps us to see what is the upper bound for the mud window. Or in other words, what is the maximum pressure that the wellbore can support. This helps us a lot in several aspects. For example, as we were saying before, to determine what is the maximum pressure that the wellbore can support, so you can design your mud window. But it's also very useful to obtain some other properties and some other characteristic values of a place, like for example the minimum principal stress, or sometimes also the permeability of the formation. All right, the pressure in the wellbore as we isolated with the packer is going to depend on several things, including the density of the mud, the depth at the location in which I'm performing the leak-off test. Basically, this is going to give me the hydrostatic pressure, and also depends on the rate and volume of injection. So here I have made an schematic of what we might expect for a leak-off test. And let me use this window in order to present this in order. We're going to start this test with an injection rate which is equal to 0. So this at time equal to 0, we are at the stable conditions, the injection rate is equal to 0, and at that point I have a pressure in the wellbore which is at a constant value. Because the rate is not changing, the pressure is not changing too. And in this particular case, this pressure in the wellbore, PW, is going to be higher than the pore pressure, so I don't have production of fluids from the formation, and it's also lower than the minimum principal stress. We know that if we are above the minimum principal stress, we might have chances of having a hydraulic fracture. And in this case, I have also assumed that we are under normal faulting conditions. All right, so let me write that. So that's going to be helpful to clarify what I'm doing over here. I'm going to rather use now this window. And we were saying that in this example of the leak-off test, we have normal faulting conditions. And under normal faulting conditions, the horizontal stress is going to be our minimum principal stress. All right, so we are at this point. Let's see. We're going to start injecting now drilling mud at a constant rate. I hope that you see that because this cavity is under near closed conditions, it's not perfectly closed because some of the mud is going to leak off into the formation, but it's going to be relatively close. Because I'm injecting a fluid, the pressure is going to increase. So PW is going to increase as I have a constant injection rate. And the question is how far this pressure is going to go. If I assume normal faulting conditions, and I also assume that the minimum horizontal stress and the maximum horizontal stress are the same, using the equations of Kirch, I can calculate that the breakdown pressure, and this is the pressure in the wellbore at which I will have a tensile fracture, is going to be, using directly the Kirch equation, it's going to be equal to the pore pressure plus 3 times the minimum effective horizontal stress minus the effective maximum horizontal stress. And here I'm going to consider also that I have a tensile strength. Let me write that again. Plus the tensile strength. Let me do that again because it's not clear. Okay. Plus the tensile strength. And if I'm in the conditions in which the two horizontal stresses are the same, I'm just going to call that sigma h, and therefore the breakdown pressure is going to be the pore pressure. 3 times sigma h minus 1 sigma h is going to be 2 sigma h plus the tensile strength. And what this equation is going to tell me that the wellbore is going to start creating tensile fractures around the wellbore whenever the pressure of the wellbore achieves this value. In graphical, these values plotted in a graph show up like this. Pore pressure is over here. 2 times sigma h will be the sigma SH min minus pore pressure is going to be sigma h. So this is going to be 2 sigma h plus the tensile strength is going to give me the value at which the wellbore is going to start to break and have a tensile fracture. That's what is called the leak-off point. At that point, the pressure is not going to increase linearly with the amount of injected volume if I have a constant rate in the wellbore, but at that point, this condition is going to start to get lost. And if you continue injecting mud in this formation, what is going to happen is that it's going to go over a little bit of a higher value, and that's what is called in the leak-off test the actual breakdown pressure of the wellbore. And at that breakdown pressure and at constant rate is where at this point a large fracture is going to form and the drilling mud is going to get into the formation. So let's take a look at that. I have some schematics here to help to see what's going on. Let me move this a little bit over here. And this is what it would happen in the formation. Let me bring it back. All right. So here we will be at the moment of the breakdown pressure. This is the maximum pressure that the wellbore can resist. I'm still injecting at a constant rate, and I go from a condition where before I didn't have any fracture to the point in which I have a small tensile fracture. That's going to be the leak-off point. Whenever I go over the breakdown pressure, I will have a large fracture and mud, which is not only leaking off from the wellbore, but also going into fractures and leaking off into fractures. All right, so after this happens, the pressure is going to decrease. And you may wonder why this is going to decrease. And what happens is that when you create a fracture in the rock, usually that's a very rapid process. And the fracture is going to open very quickly so that the cavity created by the fracture is going to be larger than the volume you can inject at a given injection rate with a typical pump. So since the pump cannot supply enough mud in order to fill this cavity, then the pressure is going to go down. That's why the pressure goes down. Once the injection rate catches up with the rate of production of new volume in the fracture, that's a point in which the fracture, the pressure in the fracture and in the wellbore is going to more or less stabilize, and you will achieve what is called the fracture propagation pressure. At this point, the pressure in the wellbore is more or less constant, and you have a pressure which is able to support this fracture growth. All right, so here there is something very important to notice. This fracture propagation pressure has to be large enough so that the fracture propagates with time. And because of that, it cannot be lower than the minimum principal stress, because otherwise it wouldn't be able to open up the formation. And it's going to be somewhat larger than that minimum principal stress, and that value that tells you how much larger it has to be for this fracture to propagate is what is called the net pressure. The net pressure is going to lump many variables in fracture propagation. We're going to see later on in detail how to calculate and estimate this net pressure, but in summary, it's going to depend on the viscosity of your fluid. The more viscous your fluid, the higher the net pressure is going to be. It's going to depend on the stiffness of the rock. The stiffer the rock, the more difficult it's going to be to open a fracture, and therefore the higher your net pressure is going to be. And let me repeat, the net pressure for a fracture in order to propagate it has to be larger than zero. We have made a simplification so far that we might have a chance of a fracture propagating in nature when the pressure was larger than the minimum principal stress. And that it is still the case, but before we were ignoring the value of the net pressure. We were considering that very small net pressures will be enough for a fracture to propagate. Well, now we know that there is going to be a net pressure which is higher than zero for a fracture to actually propagate. All right, so let's continue. What would happen now if you shut in the pump, if the rate goes to zero? You would expect the pressure also to decrease significantly. But notice that when you close the pump here, when you shut in the pumps, there is going to still be fluid in the fractures. As soon as you shut in the pumps, the pressure measured immediately after is what is called the instantaneous shut-in pressure. But that doesn't mean that the fracture is closed. Only when the fracture is closed and the mud that was in the fracture leaks off into the formation, we'll reach what is called the fracture closure pressure. And the point at which the fracture closes is going to be a very good estimation of the value of the minimum principal stress. We're going to see in a bit how we use and estimate this value of fracture closure pressure, which will be when the fracture closes back again, so that we can estimate the minimum principal stress. All right, the pressure is going to still decay with time, and that's because the pressure in the wellbore is still higher than the pore pressure, and the wellbore is still leaking off mud through the wall of the wellbore. And this is going to go down, and if we just leave it at hydrostatic conditions, it's going to go on equilibrate to the pore pressure value. Now let's do the following exercise. What would happen if we start injecting again mud in the same wellbore that has already been fractured? Well, if we were to do that, this is what we will see. We will see that the pressure will go up again. The pressure will go over a maximum value, but it's not going to go up to the breakdown pressure including tensile strength anymore, because we have already fractured the wellbore. So it's going to go over the hump and then come back to the same fracture propagation pressure that we had before. At this point, I'm going to resume fracture propagation. What you have in this schematic is what is called an extended leak-off test that goes over the breakdown pressure and goes in finding and trying to determine very well what is the fracture propagation pressure and what is the fracture closure pressure. As I was saying again, this is very useful for drilling applications because we can determine what is the maximum pressure that the wellbore can support. That's going to be the breakdown pressure. And also we can determine what is the minimum principal stress. And that will help us calibrate our models of wellbore stability as well. All right, so we said that fracture closure pressure is something very important, and that's something that we're going to determine in a few examples now. Here you just have one example with real data about what the shape of the curve, or the signature of the pressure with time looks like. And let me highlight something over here. I think this is a good time. And this is the difference between surface pressure and downhole pressure. As you can see here, in this example, we have a pressure that starts at 0. Well, in this case, this particular example is showing measurements of surface pressure. Let's explain what that is. If you have a wellbore and you're performing a leak-off test or any test at the bottom, and here you have, let me replace this for a pump. Here you have a pump which is injecting fluid into this formation. We're going to have on the surface, we're going to measure a surface pressure. But at depth, we're going to have a downhole pressure. And let's call this one DHP for downhole pressure. Okay, the downhole pressure, which is an absolute value, is going to be equal to the hydrostatic component for example, in a case of drilling, this will be the density of the mud times G times the true vertical depth plus the surface pressure. Let me try that again. So, for example, when the surface pressure is equal to 0, that means that the downhole pressure is going to be equal to just the hydrostatic component. When the surface pressure is larger than 0, that means the downhole pressure is higher than the hydrostatic component. This is something very important to take into account in practice, and something that we're going to see when we talk about solving some practical problems. But remember, in this example, this is a surface pressure. And so it's going to be in the cases which I'm going to show now for determine the instantaneous shedding pressure and the fracture closure pressure. Okay, these two values, the instantaneous shedding pressure and the fracture closure pressure, are going to be very important, and they're going to help us determine what is the minimum principal stress in locations where we have this leak-off test. Let's go first with the instantaneous shedding pressure, and here we have an actual example with field data. On blue, we have the surface pressure measured on surface and the rate of injection, which after minute more or less 71 is more or less constant and equal to a value of 30 to 35 gallons per minute. All right, so let's make a zoom in this area, and what we observe is that when the pump shut-ins and the rate is equal to 0, the value corresponding to that instantaneous shut-in pressure is the one that is right here. So once the rate again is equal to 0, we assign the value of the shut-in pressure to that corresponding surface pressure reading. In this case, that instantaneous shut-in pressure is 959 psi. The instantaneous shut-in pressure is going to be very important to determine because we also want to know what is the time at which that instantaneous shut-in pressure occurs. As we're going to see, this is going to be useful to determine the fracture closure pressure. All right, in order to determine the fracture closure pressure, what we do is we obtain this data after the shut-in pressure, and we define the time of shut-in as time equal to 0. And we're going to plot the surface pressure as a function of the square root of that time. That's going to be the time at a particular point, let's say somewhere over here, minus the time of the shutting in the pumps, and to that square root. When we do that, we will observe that the pressure is going to show a characteristic signature. And this signature is going to vary more or less linearly with the square root of time when the fracture is open, because that means that this is a linear type of fluid flow in which the fluid is leaking off from more or less a line instead of a point. Let me clarify that by doing a schematic of this. In the first case, if this is our wellbore and we have a large fracture, the leak off is going to be similar to coming off a line or a linear feature, which is much longer than the well. Under these conditions, we are going to see that the surface pressure is going to be linearly proportional to the square root of time. That's why you see that in this trend, we can fit that to more or less a line. And here I have highlighted those points in red. That's the linear part of the signature. Once that signature deviates from that linear trend, that means that the flow regime changed. And in this case, the flow regime changed to something more of a point or radial leak off. You may expect that it's a lot easier to leak off fluid from something larger, like a fracture. That's why the pressure goes down quickly than leaking off from a point. A point is going to have a lot less surface area, and that's why the pressure is going to leak off or is going to go down more slowly, leaking off less and less mud. The transition from here to there is what indicates the fracture closure. So at the point that the fracture closes, even though the fracture might be present, and let's try to draw that, even though the fracture is present there, it's already closed and it's not leaking off any more mud from the fracture, but mostly from the well. And that point is going to determine the fracture closure pressure. In this case, more or less, this is the point. And if you go through the y-axis, you can extend that and you can obtain what is that fracture closure pressure in terms of surface units. If you really wanted to know, in this case, what is the minimum principal stress, let me bring this back again. We said that fracture closure pressure, we're going to approximate that with the minimum principal stress. So in this case, if you wanted to know what is the value, absolute value of the minimum principal stress in downhole conditions, remember, you will have to add the hydrostatic component or the weight of the mud. There is another test that it's very useful for well testing, and let me come back here to my list. This is going to be the DFIT test. The DFIT test is going to be used for completions, and it's actually very similar to the leak-off test. The difference is that DFIT test is not done with drilling mud, but is done with a fracturing fluid, and also the DFIT test can be done with an open hole, but also can be done with a cased and perforated hole. For example, for creating hydraulic fractures out of a cased wellbore and perforations, that's what we want to do. We want to perform this diagnostic fracture test with a cased wellbore and out of the perforation instead of from an open hole wellbore. Another difference is that in the DFIT test, we are going to use much smaller quantities of volume injected in the formation, usually less than 10 barrels. And the injection rates also, since these are relatively small fractures, are going to be relatively small. We're not going to go into detail about how to analyze the DFIT test. The analysis is very similar to what we saw for the leak-off test, but there are some other types of analysis that use, for example, what is called the G function, based on similar flow regime concepts to what we were showing before, that are useful to determine what is the fracture closure pressure. For example, you can see in this example that the crossing of the G function and this other derivative curve tell you what is the value of the fracture closure pressure. Again, we're not going to go into detail about this because there are different procedures. Some of them are better than others, and depends on the application, depends on the kind of rock, but the concepts are very similar. What we have to know is that the fall off of pressure with time can allow us to determine what is that fracture closure pressure. And one more thing about the DFIT test is that the DFIT test usually is done, as we were saying, for completions, and therefore, in this case, is very popular for unconventionals. In order to measure minimum principal stress in unconventional formations, this is what you use. And again, it's very similar to the leak-off test, but in this case, we use fracturing fluid and much smaller values of fluid injection. All right, let's go to the third example that we have, and this is the step rate test. The step rate test is used for applications of fluid injection, fluid disposal, and also for enhanced oil recovery. The step rate test, therefore, is not going to inject drilling mud or a hydraulic fracturing fluid. In this case, in the step rate test, we are going to inject the particular fluid we may want to inject in a particular formation. So this could be water, for example, for water flooding. It could be also be vapor for steam injection. It could be carbon dioxide, nitrogen, methane, polymers, foam, and produced water, any type of fluid that we may want to inject into a formation, for example, to displace another fluid, to maintain pressure, or to get rid of it. So let's see how this step rate test is done. Here the objective is to determine what is the rate that is going to cause fracturing in the wellbore. And in order to do that, what we do is to increase the injection rate in steps so that we can figure out what is the rate that causes that wellbore to be fractured. And this is more or less the procedure. What you would do is to set different rates of injection, as you can see in this figure, as a function of time. First, you inject at a given rate, then you increase it again, and again, and again. When you do that, you would expect your pressure, downhole or surface pressure, to increase with time. This pressure is going to increase and is going to equilibrate with the pressure in the formation that it's in equilibrium with that rate. At this condition, where the pressure is more or less constant, is when you achieve steady state. When you double, for example, in this case, the rate, you should expect a similar increase in pressure. And there is going to be a point where this incremental change of rate is going to cause an incremental change of pressure, but at some point that pressure is not going to be proportional anymore. Let's see what is the cause. Here is the result, and before we go through that, let's remember what is the wellbore equation. We know that the flow rate is going to be proportional to the difference in pressure between the wellbore and the far field. So if you were, for example, to double the injection rate, you should expect to double the difference in pressure. Unless something else happens in the wellbore, if you assume all of these parameters to stay the same, like viscosity or permeability of the formation, the only thing that could change here is the skin factor, which would tell you that if you have a fracture or not, because your skin factor is going to change dramatically. So in coming back to the plot now, what we would expect is a behavior like the one we have over here. Now we plot here the injection rate in the x-axis and the difference in pressure in the y-axis. When the wellbore is not fractured, the difference in pressure should be linearly proportional to the injection rate, as we saw in the equation of the wellbore. However, there is going to be a point in which increasing the rate is not going to result in the same increases of pressure. And we can see that result in this schematic with these 2 points. And therefore, at that point, there is a transition going from a wellbore that is not fractured to a wellbore which is fractured, and now is leaking off fluids out of the wellbore and the fracture as well. If we trace lines that join the first trend without a fracture and the second trend with a fracture, we are going to obtain at the intersection of these 2 lines the fracture parting rate and the formation parting pressure. So this is the rate at which you will create a fracture according to this particular test, and that will be the characteristic pressure. In many wellbores and in many cases of injection, we do not want a fracture to happen. For example, because you just want to get rid of a fluid and you don't want to fracture the injector. In many applications of, for example, EOR, you may want to avoid fractures, so your sweep efficiency it's not affected by the presence of a fracture. In some other cases of disposal of some fluids, if you want to apply for a permit to dispose water, you have to prove that your wellbore is not going to be fractured. So in this case, you also run a step rate test. And the objective is to determine what is the maximum rate that you can use in that wellbore so it doesn't fracture. Here I have one example. It's very obvious in here the change. This is actual data from a steam injection project off the coast of California near Santa Barbara. And you can see how the injection rate increases more or less linearly. The pressure increases more or less linearly with increase in injection rate, but there is a certain point at which if you keep increasing this injection rate, the pressure is not going to increase that quickly as it did before. At the intersection of these two lines is where we have the formation parting rate and what tell us what is the maximum injection rate which we can inject. Let me emphasize again that the step rate test is a test that is used for injection of fluids. We mean to inject fluids in a regular manner and sometimes 24/7. So in this case, what we want to determine is what is that maximum injection rate. And here, before I go to the last example, let me tell you some things that are not captured by the injection, the step rate test. And usually with the step rate test, we inject a small volume, so they do not capture the increase of pressure with time over very long times. So, for example, you may run a step rate test over a week and determine an injection, maximum injection rate and a maximum injection pressure, but that doesn't mean that that's going to work for 1 year or 10 years. In some cases of a very long injection, the pore pressure in the formation may also increase with time, and also that may produce an earlier fracturing of the injector at a particular location. So that's something very important to consider. And also remember that sometimes if we increase the pressure too much in a particular place for a long period of time, we can also cause fault reactivation. The step rate test is just related to the fracturing of the injector with a hydraulic fracturing at the injector. All right, so we were saying that in most times we do not want to cause a fracture at the injector when we are injecting, for example, fluids for EOR. However, there are some cases in which a fracture in the injector might be good. Here in this example, we see an application under normal faulting conditions in which, for example, if you have an injector here at the bottom and a producer here on the top, and this is your condition of a state of stress, if you were to fracture the injector, that fracture will go directly into your producer, which is not good because any fluids that you inject will not sweep the formation, will not push any remaining oil, but will go directly to the producer, and you're just going to produce what you're injecting. Let's say water or a foam or a polymer. So this would not be a desirable case. But in some other times, you could take advantage of your fractures. And in this case, if we were to place the wells differently, and in this case have the wells oriented such that if you fracture the injector, that fracture is perpendicular to the line that joins the two wellbores, then you may help sweeping some of the fluids in the formation because now your hydraulic fracture is not extending towards the producer, but rather is extending away from the injector into the formation and reaching further where probably the wellbore cannot reach. And so you have a more controlled sweep of the rock in this case, and it doesn't go into the producer, but rather goes into the rock and reaches a bigger surface area. All right, this is the end for the applications of hydraulic fractures in well testing. So far, we have just seen phenomenologically how these hydraulic fractures happen in well testing. In the next chapters, we are going to see how we can predict these particular rates or pressures at which these hydraulic fractures are going to form.